Hello, thank you for coming. My talk is about simplicity to its extreme. And to make it brief, the take-home message of this talk is good physics is simple. And I'm glad that a few people still agree with me on that. But the question is actually, what does simplicity mean in physics? And I will try to give you a definition, but maybe we can learn also a little bit from examples. And according to particle physicists, the most simple description of reality is up quarks, down quarks, chunk quarks, strange quarks, bottom quarks, up quarks, 3 colors each, electron neutrinos, mu neutrinos, tau neutrinos, W bosons, Z bosons, Higgs bosons, and so on, gluons, and so on, and so on.
The Higgs boson is not the
Yeah, that's another complication. Yeah, but without the Higgs boson, it's very simple, isn't it? Yeah. Thank you very much. Professor Hale, I didn't see you before. I'm glad you're here. I learned a lot of things from him. Well, there were reflective voices in particle physics. If I could remember all these names, I would have become a botanist. Enrico Fermi, but I think the reflective voices are dead. And but certainly that reminds us from another reflective voice. If the Lord Almighty had asked me before embarking creation, I should have recommended something simpler. This is King Alfonso of Castilla, and he said this when he visited the library of Toledo and discovered that medieval astronomy was described by epicycles. And certainly this current model of physics reminds us from epicycles. And well, I think this is a crisis in physics. And if you really believe that physics is fine and the standard model is the best thing we have, and presumably I can't help you. But we have other complications in physics too. Also, the standard model of cosmology is going towards complication. 95% of the universe is assumed to be invisible. That's a little bit worrying. And but there are even more parameters, free parameters. Mike Disney, an astronomer, says that we have 17 free parameters in cosmology and only 13 independent observations. The situation is far from healthy. And particle physicists usually they don't count even more than free parameters, if you include the masses of elementary particles. Now, what are masses of elementary particles? I've just listed the most important ones, but these are real rules of physics. Why is the proton 1,836 times heavier than the electron? Why is that? I mean, of course, the Higgs boson has given the answer. It's because the coupling is 1,836 times stronger to the Higgs field. If you think this is a good answer, that's okay. The fine structure constant is a very important number. And if we reflect about physics, I think we should try to calculate these numbers. I think we should not give up to understand these numbers. Dirac said, if somebody arrived and said, I have a new theory, can you calculate the fine structure constant? No? So come again when you have it calculated. And Richard Feynman said the same thing. It's a magic number. It's one of the damned mysteries of physics, a magic number that comes to you with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. We know what kind of a dance to do experimentally to measure this number very accurately, but we don't know what kind of dance to do in a computer to make this number come out without putting it in secretly. All good theoretical physicists put this number up on their wall and worry about. So, I think this is pretty much the same point of view as Einstein expressed it in a very interesting conversation. interesting letters he exchanged with Ilse Rosenthal-Schneider. And I think they had the right kind of philosophy. Numbers arbitrarily chosen by God do not exist, and their alleged existence relies on our incomplete understanding. And this is what I think history tells us. Whenever we postulate a new free parameter, we just describe, and when you're able to reduce the numbers, you understand. Thus, I think there is a very simple measure for simplicity: the number of fundamental constants in physics. And I said that the actual number is worrying, but the other question that comes up is, well, what is simplicity? But the other question is really simplicity good physics? And I think it's not a personal fancy of mine, but actually we have evidence that simplicity drove the real revolutions in physics. All real progresses in physics were related to the reduction of numbers. While on the other hand, if you do normal science, we find an anomaly, we fix it by a free parameter, and the system is just a little bit complicated. And I think we have plenty of examples of such free parameters that are kind of excuses, notions that have proved to be useful for ordering phenomena, easily gain such an authority that makes us forget their mundane origin. We are tempted to accept them as irrefutable laws, but by such errors, scientific progress is often hindered for a long time. I can think of quarks, and you may think of dark energy or something like that. And I think it's true that we should not take too seriously these concepts. And Erwin Schrödinger expressed it beautifully: once a problem is removed by a feeble excuse, there is no further need to ponder over it. If you think about concepts like confinement in quark physics, I think that precisely hits the point. Now, instead, paradigm-changing revolutions in physics, they were always related to a reduction of the number of physical constants. And as I said, this is evidence from the history of science. I think history of science is as such an observational science. And we observed that the big breakthrough of electromagnetism is the reduction of three constants to two. The magnetic field and the electric field constant are related to the speed of light. That's a great discovery. And why it's a great discovery? Because it reduced the number of fundamental constants from 3 to 2 and unified electrodynamics with optics. So why is quantum mechanics a revolutionary discovery? Because we observe these Planck's quantum in various instances. We observe it in light, we observe it in atomic physics, and in many other effects. It's just described by one constant. That's a tremendous simplification. And of course, a tremendous simplification was Newton's law of gravity that made obsolete all the epicycle parameters of medieval astronomy. There was just one gravitational constant to which all these numbers were condensed. So if you think about that, complication is the number of fundamental constants, and good physics needs less constants. What are the most fundamental constants? And I think we end up with the gravitational constants, with the speed of light, and Planck's constant. And I think there is a very interesting idea, and unfortunately I don't have the time to talk about today, but there is a very interesting idea to get rid of the gravitational constant. I had a talk about this yesterday. It's actually cosmology inspired by Einstein with a variable speed of light, Robert Dicke, and Paul Dirac. So, well, if you just look at the units, if you take the sum of all masses of the universe and divide it by the respective radius and c squared, that gives you the unit of the gravitational constant, and that's what usually is called flatness of the universe, this coincidence. Okay? But there is in principle a possibility, and well, I skip this because what I want to do somehow ambitiously is to focus on the well, I forgot to mention this is also related to another very interesting number in physics, to Dirac's large number hypothesis, that would deserve another talk. But what I want to do is to focus on the remaining constants, h and c, because I believe these two are the most fundamental ones. And again, I quote Einstein, I cannot imagine a theory containing an arbitrary number which could have been chosen by the creator in just another way. So if you look for a fundamental theory of physics, we should try to get rid of all constants, even if this sounds very ambitious, even if this sounds crazy. And the question comes up, are C and H actually anomalies? Are these just free parameters? The speed of light and Planck's constants may indicate a failure of Newtonian physics of classical mechanics. Because, well, there has to be a reason. There's no mathematical reason why you need C or H. Newton didn't know anything about it. Newtonian physics works perfectly without C and H. So why is C and H there? Nothing is created by coincidence. Rather, there's reason and necessity for everything. There's no reason why matter should not be accelerated beyond the speed of light. So you might look at the constant c, the speed of light, as an anomaly, as something that falsifies Newtonian mechanics in a way at the large scale. And equivalently, there is no reason from classical physics for discontinuous phenomena, and there is no explanation why physics shouldn't work at the small scale. By the way, I ask myself, why don't mathematicians protest against this behavior of physics? They have so nice concepts like continuity and differentiability, and physicists muddle around and say, okay, these things that don't work very well on the small scale, so you have to consider quantum effects, that's it. But there is no reason why the constant h is necessary at all. And there has to be a justification. And if you think about what are the axioms of Newtonian physics, that's the existence of space and time. He didn't question that. He said, okay, we have three-dimensional space and an invisibly river called time flowing. So, by the way, of course, you're tempted to say, okay, we have relativity, we have quantum mechanics, and these are brilliant theories, wonderful theories, because they're efficient theory to a certain point. But they still describe physics, the phenomena, with a free parameter. And relativity very elegantly describes the deviations from Newtonian physics by introducing C. But it's still a description. It still doesn't give a reason why C has to exist at all. So we might question the notions of space and time itself and think about how many problems of physics might be, well, if space and time aren't the proper notions we're discussing physics, so many problems maybe are just ill-posed, such as wave-particle duality, and so on and so on. I'm not going to make friends here, people who are dealing with these problems maybe. But I really believe that many of our problems in physics just could arise from these inadequate notions of space and time. Because there is no a priori reason why space and time should exist in this particularly 3+1 dimensional form. So there are long conclusions. I still have a little bit of time. The line of argument is good physics is simple, and obviously the standard models of cosmology and particle physics are not very simple. Real progress in physics has always eliminated arbitrary numbers, and consequently a complete theory of reality must do without any constant of nature. And C and H, the most fundamental constants, even these two, can be seen as anomaly that cast doubt on the validity of the axioms of Newtonian physics. By the way, space and time are very different things. I think it's a misguided approach in physics to call it just 4 dimensions. Oh, there's a proportion constant C you don't think about. No, time is very, very different from space. That's a fashion introduced by Hermann Minkowski in 1908. He said, oh, we really live in 4 dimensions. But it's not true. You can't navigate through time as you can in space. It's very, very different. So, and there is no reason why reality should have such a peculiar 3+1 dimensional structure. Rather than about the origin of space and time, maybe one has also to wonder about the phenomenology of light and matter. Why does nature present itself with these distinct two phenomenologies? Obviously, C is related to light and H is related to matter. And if you want to understand these two constants, we need to answer this. And, well, so to conclude with a little bit of speculation, a tangent space of a 3-dimensional manifold may create the illusion of a temporal, of an additional dimension. If you just imagine a tangent space on a sphere, and you move along the sphere, so every tangent space is different. So in every instant, you're observing a new world. And if you're walking around the manifold, and you see 1 dimension more, it's not real. It would be still a sphere, or it could be still a 3-dimensional manifold. And C and H are presumably entangled in a subtle way when creating the phenomenology of space and time. And I think, well, it could be that we must find purely mathematical properties that create this necessity of C and H. And if this is the case, it's going to be very hard for physics because, of course, there are lots of things you have to fix if already the concept of space and time, if something is wrong with that. So it's the book of nature written in mathematical language, and if you know what I think about string theory, you might be amused by the fact that I think it is. I think the book of nature is written in mathematical language. So I think we have to look for mathematical structures that might create the necessity for C and H. This would be a real breakthrough. And well, I'll stop here. You can look up the cosmology part in this paper, and you might find a few of my thoughts in this book, Bankrupting Physics, which is an English edition of this book of the year in 2010. And there is another book about the crisis in German and about the complication of particle physics here. Thanks for your attention. Thank you. Okay.
What would you recommend physicists of the next generation? What should they do?
Stop and think. Oh, no, it's very spontaneous. Yeah, I think physics is really a great science, and I think we have terrific findings at the beginning of the 20th century. But I think every young physicist should be aware of the crisis. And the problem is you have to rely on authority if you want to go ahead. So it's a hard time for people thinking with their own brains. And there are lots of things I could say with the methodology. I think there are very interesting experiments, particularly in space physics, space-based telescopes, and I think it's a fantastic time. It's a fantastic time with respect to the data. So if all the data is public and all the data is transparent, and if you're able to present the raw data without any theoretical prejudices, then you might have a good time as a young physicist too.
Dennis? You said that every big revolution came together with a reduction of the fundamental constants. I don't see that at all. I mean, some of them did, but some revolutions were precisely brought about by the discovery.
Could you talk louder, please?
I'm sorry, I have.
Yeah, I will try to resume.
So you said that every big scientific revolution came together with the discovery of a reduction of the fundamental constants. That is true for some scientific revolutions, but definitely not for all of them. Especially some that you mentioned. I mean, quantum mechanics is the discovery of a new fundamental constant, of Planck's constant, but there is no reduction of other constants to Planck's constant.
No, I tell you.
Okay, let me finish. And special relativity, in comparison to Newtonian physics, is the discovery that there is a new fundamental constant, a barrier, that a limiting speed that no material particle can pass. That wasn't there before, and it's not really clear that the number of fundamental constants is reduced. So, I mean, it's true it happened in some revolutions, but I think it's too far-fetched to grant a claim to say for every revolution that happened, it came together, it was brought about by a reduction of fundamental constants.
Okay, I mean, obviously people have different notions of what is a revolution. I mean, there are also people claiming there are revolutions in string theory.
Right, but those that I mentioned,
Okay.
special relativity, quantum
So,
mechanics.
but with respect to your comment on quantum mechanics, it's a little bit subtle, but the point is there. If the very beginning of quantum mechanics is atomic physics, is Johann Jakob Balmer, who observed that the spectral lines were all related to the inverse, and then you have Balmer's constant, okay, but which was an arbitrary constant, which nobody understood. And the first one to understand Balmer's constant was Niels Bohr, with the help of Planck's constant. So this was just one of the one instant where there was a reduction, because Balmer's constant was obsolete from this point.
Okay. With the Stefan Boltzmann law, there was a couple of constants, and they were reduced by reducing the age.
That's another
so
example.
The age really reduced a number of constants. I think this example is really a counterexample to what you say.
All right. How about special relativity? What fundamental constants are reduced to the speed of light?
I mean, I agree that people will disagree, but I wouldn't even call special relativity a revolution in that sense. Okay? Because, I mean, you had a phenomenology which contradicted. Physics was a mess before it, because nobody understood. There was Lorentz claiming that E equals 0.75 mc squared, or things like that. So there was a big mess. And well, one possibility that was that other people made up artificial constants out of this mess. And Einstein, with a brilliant move, saw that he could explain it with just one constant. I admit it was existing, what is existing constant. But my point is, so it's a very good theory in the sense it needed just one constant. Yeah? And for that I appreciate it. But still, if you look at Newtonian physics, there is no need for this C. No need at all.
Newtonian space-time has no fundamental constant, and special relativity has one fundamental constant, C. So in that sense, it's one more constant.
Yes. Mm-hmm.
Okay, Meinert?
Yeah, simplicity proved to be a very powerful heuristic principle in the formation of physical theories. But isn't it, in the end, just only a heuristic principle and nothing more? I mean, simplicity, I think simplicity is attractive. We think it's not only powerful, but it's a very attractive principle. It's connected with beauty. We think that simpler theories are more beautiful. And of course, beautiful theories are nice, for sure. But if the correct theory turns out to be not so beautiful and not so simple, then be it so.
Okay, it's good that to talk about, because what is simplicity? It's a good point to discuss. And certainly, I don't think that simplicity means beauty. And I don't think that simplicity means mathematically easy. No. I would just propose a very pragmatic way. Simplicity means reducing information. When Mozart listened to a symphony, he was able to write it down just after he listened to the concert. Why? Because there was a simple structure in the music he was able to understand. He couldn't memorize all the musical notes. That would have been impossible for physical reasons. But there was a structure he understood. So simplicity is extracting the information. If you have raw data, you have gigabytes and gigabytes. But the art of understanding is to reduce the information, to make smaller and smaller bits of important constants, and ultimately to get rid of the constants at all. That's my
our goal is to
conviction.
find a correct theory, not a simple theory, isn't it?
I think
It might help in our pursuit of the correct theory. It might be helpful to look for simple theories, but that's in itself not the goal.
Yeah, I mean, what is correct? You can claim that epicycle astronomy was correct. And if you added another dozens of epicycles, it was still correct. But it's not satisfying. It's not the point. The fewer information,
We have one more
the
question.
fewer information you're able to make out of the data, the more you understand. Otherwise, you just describe, with a lot of parameters, you just describe. Physics is about understanding. We want less parameters. We want to calculate it to understand.
Okay, we have time for one brief last question.
Actually, there's two, but I'll try to be quick. It's regarding your definition of simplicity. You reduce it to the constant and you say that it doesn't matter about the model. But I have an objection about that. It's like using the same analogy that you said with writing down the music would be very simple. But of course, if you complicate your language, you can express things with a very simple, very few words of that language. But maybe you have to complicate your language arbitrarily a lot in order to obtain and be able to do that. So if you reduce the number of constants, but you let people choose whatever model, you can always construct a very complicated model that is self-contained and doesn't need any constant, but it will be a very complicated model for which maybe you need a very complicated language. So I'm not sure that's simple at all, and I think it should be also taken into account besides the constant. And the other comment, it's about the anthropocentric principle, because that would play a role also, right? Maybe you live in this world, it's like this just because it's the only world. Well, it's possible to have an Earth where there are humans, blah, 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 etc. So I wanted to comment, so that you comment on this.
Okay, I try. Well, your first point is if you're able if you postulate a language which is complicated enough, you can always have simple formulas. And there is a beautiful there's a beautiful joke by Richard Feynman who says the formula of everything is just the sum over ui is 0, which this means the deviation from a law of physics and the family of laws of physics. So this is the world formula. Now that's a joke, of course. You can easily detect if the language is too complicated. I had a discussion with a particle physicist who said, well, it's so simple. It's just SO2 and SO3 and something. Isn't that wonderfully simple? So, but it's, well, if you look at the trash bins out there, you have 3 things, yeah, but it's not necessarily simple what's going in there. You can put simple structures, but you easily find out what is simple and what is not. I don't think this is the problem. And so my point was really anomalies or complications always arise if you don't understand a basic concept, which might be space and time. And your second point is, should I comment on the anthropic principle? What, I think this is a departure from science, because well, why is the fine structure constant 137 and not some other? Because there are other universes. So what? Yeah? There are other universes. There are maybe at the Big Bang, at the period of inflation, there are multiple universes. So you don't have to explain anything. But I think physics is about explanations. I mean, we live in a time where we have problems, where physics has problems. I mean, the day after tomorrow, I think the Max Planck medal is awarded to the so-called results of inflation. I think that Max Planck will spin in his grave if you looked at these results. But that's what we call physics today. Yeah. That's the situation we are in.
I think that's a good conclusion. Thank you very much again.